This lesson is on the standard normal distribution, and the standard normal distribution is a normal distribution with a mean of 0 and a standard deviation or a variance of 1. We write our standard normal variables we normally call as Z, and we say they're distributed with a normal 0, 1 distribution. And remember, 1 stands for your variance, but in this case the standard deviation is the square root of our variance, and that will also be 1. We're going to start by looking at a quick reminder of how to code data. So coding data is just transforming it in some way. So as an example, I've written a variable x and I've got 5 values for x and they add up to 100, so my mean value is 20 and my standard deviation I'd have to do on a calculator is 7.16. Now I've made my variable w to be x plus 10, so I've added 10 to all of these values. Now that's going to mean that they add up. Instead of adding up to 100, they're now going to add up to 10, 20, 30, 40, 50, more than that, so 150. So my mean for x is going to be 10 more than what it was, which is 30. So if I add 10 to every single value, it adds 10 to the mean. It's not going to have an effect on the standard deviation because the spread of the data has not changed. So because I've added 10 to every single value, I've just transformed them all upwards by 10. I haven't changed how spread out they are. If, however, I multiply all my values by 3 instead, so if this variable, I've called it z, which isn't very good because that's normally the standard normal distribution, but I've multiplied all of these values by 3. That is going to make everything 3 times bigger, so the mean is going to be 3 times bigger, so it will now be 60. My standard deviation this time will have changed. So because I've multiplied all of the numbers by 3, they've all got bigger and are going to be more spread out. So the bigger numbers will have got bigger by more than the smaller numbers. So my standard deviation will also have been multiplied by 3. So I'm going to get 7.16 times 3, I'm going to get 21.5-ish for my standard deviation. Now normally, or usually, if we've got a normal distribution, we say that it's distributed with a mean of mu and a variance of sigma squared. Now I can code that data to give me a mean of 0 and a variance of 1. So if I take my values and I take mu off all of the values, then my mean will go from mu to mu take away mu, which is 0. If I divide that by anything, that's not going to change my mean because 0 divided by anything is still 0, but it will change my standard deviation. So if I divide this by sigma, my standard deviation will go from sigma to sigma divided by sigma, which is 1. So if I code my data by taking away the mean and dividing by the standard deviation, my mean becomes 0 and my standard deviation becomes 1, so I will now have a standard normal variable. So this is called standardizing. So I'm coding the data to give me the mean and the standard deviation required to make it a standard normal distribution. So this is explained to us in the notes for this lesson. So it's often useful to standardise normally distributed random variables by coding the data to get a mean of 0 and standard deviation of 1. And we do this using this. That should really be a capital X there. So all the values will now have a mean of 0, a standard deviation of 1, and there's just a little bit of notation here that we use this capital phi symbol, phi, which is an old Greek letter. Capital phi of A would be the probability that your standard normal distribution is less than A. So we can do that on our calculators in the same way as we were doing different normal distributions in the last couple of lessons. So these first couple of examples don't require us to use our calculator at all, because they just want us to write some probabilities in terms of phi. So if x is a normally distributed random variable with a mean of 50 and a standard deviation of 4, so mu is 50 and sigma equals 4, then we can code that to get a standard normal distribution. So we can standardise it by taking away the 50 and dividing by sigma. So if we want the probability that x is less than 53, that's the probability that z is less than 53 minus 50 divided by sigma's 4 in this case. So that's the probability that z is less than 0.75. So in the notation using the phi symbol, that's phi of 4. So that's all we're doing here. That was part A. Part B, the probability x is greater than or equal to 55. Remember, that's 1 minus the probability that x is less than 54. And if x is less than 54, then z is less than 54 minus 50 over 4. So that's the probability that z is less than 1. So we're looking at 1 minus phi of 1. Question 2, we're looking at a normal distribution with a mean of 14.1 and a standard deviation of 1.7. Remember, we write the variance in our notation, so it'd be 1.7 squared in the notation. So for part A, if we want the probability that x is less than 17, remember to normalise this. We are going to, to standardise it, we're going to do those values, take away the mean divided by the standard deviation. So this is going to be the probability that z is less than 17 minus 14.1 over 1.7. So I think that's better as a fraction. That's the probability z is less than 29 over 17, or phi of 29 over 17. For part B, the probability that x is greater than 8, that's 1 minus the probability that x is less than 8. And then if I standardise this, that means z needs to be less than 8 minus 14.1 over 1.7. Which is 61 over 17. Oh, sorry, minus 61 over 17. So that's 1 minus phi of minus 61 over 17. And then for part C, we want the probability that x is between 16 and 9. So if I start by standardising this, so 16 minus 4, that's not very good, is it? I want 9 on that side, 16 on that side. So I'm doing 9 minus 14.1 over 1.7 is less than z, is less than 16 minus 14.1 over 1.7. So my z values are going to be minus 3 and 19. 19 over 17. And that will be the probability that Z is less than 19 over 17 minus the probability that Z is less than minus 3. If you think about your bell-shaped curve for the standard normal distribution, 0 will be your mean, so that will be your middle value. So if we want it to be between minus 3 and 19 over 17, we're looking for this area here. So I can do the whole area less than 19 over 17, take away the area less than minus 3. So that's phi of 19 over 17 minus phi of minus 3. So sometimes, like with other normal distributions, we need to be able to reverse this. So sometimes we might be given the probabilities and we need to find the associated Z values. And we can do that using the inverse function on our calculator, or we can do it using this percentage points table, which is given to you in your formula booklet in your exam. And it gives you Z values such that the probability of your random variable being greater than that value equals this probability. So the example that's been picked out here is looking at the 2.5%, so 0.025 probability, and that has a Z value of 1.96. So the probability that a random variable is greater than 1.96 is that 2.5%. Now, because your standard normal distribution is symmetrical about 0, if the probability that it's greater than 1.96 is 0.025, then the probability that it's less than minus 1.96 will also be 0.025. So because our mean is 0, we get that nice symmetry with our positive and negative numbers. It also means if this is 2.5%, this will be 97.5%. So the probability of being greater than minus 1.96 is 97.5%, and the probability of being less than 1.96 is 97.5%. So let's use this to solve the problem. The systolic blood pressure of an adult population is modelled as a normal distribution with a mean of 127 and a standard deviation of 16. A medical researcher wants us to study adults with blood pressures higher than the 95th percentile. So that means that whatever value we're looking for, the probability that x is less than that value is 95%, or 0.95. That means the probability that x is greater than that value is 0.05. Now, our percentage points table tells us about the standard normal variable, and the probability that that is greater than a value at being 0.05 means the value at 0.05 is 1.6449. Now we standardise by taking away the mean and dividing by sigma. So to unstandardise, we will multiply by sigma and add mu. So to get the x value from the z value, we are going to do 16 times that 1.6449 and add on 127. And we get 153.3. So the minimum blood pressure for an adult in the study go for 3 significant figures. And let's put the units on there. I used X for this. Should really have used S because they've used S in the question. But as we were just going to write it in context at the end anyway, it didn't really matter what letters we used in our working.